Good evening and welcome to this webinar given by the Institute of Engineering and Technology entitled The Strange Neighbourhood of Black Holes. So welcome. This is presented by the IET's Anglian Coastal Network, which represents members in Suffolk, Norfolk and North Essex. But we welcome also people from many other parts of the United Kingdom and indeed globally. I'm delighted to welcome you all. I'm George Williamson. I'm a member of the committee of the Anglian Coastal Local Network, and I will be your host for this evening. So without further ado, I'm delighted to introduce our speaker, Dr. Ed Friedman. Ed is from Washington, DC. He graduated from the University of Maryland in physics, bachelor's, and Wayne State University for his PhD. And he has had a 48-year career working for several aerospace and non-profit companies, acted as a consultant to NASA and the US National Academy of Sciences. He has been adjunct professor in the aerospace department for the University of Colorado. He is the author of several books, and he's currently a volunteer lecturer to elite high school students on topics in physics and mathematics, and lectures regularly for cruise ships. So I'm sure that Ed can make this interesting subject accessible to many people who are not specialists in the area. So without further ado, I will switch off my video and audio, stop sharing, and ask Ed to start his presentation.
Indeed, I'm Ed Friedman, and I want to jump right into this presentation. Here's what I hope you will get out of our presentation. By using a graphical technique rather than math, we are going to explore issues of causality near black holes. Now, what does that mean? It means how event sequences occur in the vicinity of a large massive object. And I'll explain the details as we go along. But we're interested in what happens if I do something and then you observe that at some other time. How does that all unfold when we're in the neighborhood of something as bizarre as a black hole? And we're going to use two characters, Alice and Bob. These are the traditional names given to descriptions of astrophysical phenomena. And we're going to watch what happens as they have adventures near the black hole. And we're actually going to have Alice as the braver of the two astronauts. She's going to be the one that gets close to and eventually enters the black hole. And we want to talk about what Bob will observe as this goes on and what experiences Alice will have in the vicinity of the black hole. They're going to be sending messages to each other during our thought experiments. And all these messages will be sent using light beams. We're also going to look at the possibility that they both enter the black hole, and we'll see what happens there. So here's a map. This is a typical map of my neighborhood, and I want to exploit this kind of map to show you how we have to modify maps for conversations of the type we are going to have. This is a typical map of 2 dimensions in space, but it does not include time. And we have to do something about that because the issue of being near a massive object has to accommodate the fact that the mass of that object is going to change how time advances for someone near the black hole and someone farther away. So what I want to point out to you is there are 2 towns here, Boulder, Colorado, and Longmont, and a small town between called Niwot. We're going to redraw this map like this, so that the line between Boulder and Longmont with Niwot in the middle is now drawn to include a time axis. And the idea here is that we can mix together time and space when we use this kind of map. Now, a vertical line on this map indicates that Boulder, the town, is not moving. There's an arrow here to indicate that time is advancing for the town of Boulder, similarly for the other towns. But any vertical line indicates no motion on this map. So I'm redrawing it here, and we're going to use special units in a version of this map to make it convenient for our conversation. And that is, time will be in seconds, but distance, instead of being in miles or kilometers, will be in light seconds. And this has the advantage of identifying a diagonal line, a 45-degree line, either way, indicates the speed of light, because light advances 1 light second every second. Now, if you have a car driving from Boulder to Longmont, it will take a long time, many seconds, to make that trip. A rocket will improve or shorten the time required, and a light ray is the fastest way to communicate from Boulder to Longmont. Notice how a non-moving position like the town has a vertical line. The car has a slightly tilted line on this map. The rocket is more tilted, and a light ray is tilted to 45 degrees. When we accommodate Einstein's theory of relativity, we find this is the steepest that any line on this map can be. It can be either way, but we cannot have any object or light moving with a slope like this, because this implies communicating or moving something at faster than the speed of light. So we have this map, and we can, and I'll point out that this is a one-dimensional axis here. That's a straight line between the various towns here. We can do a little bit to try to add another dimension to this, because we're always challenged in these kinds of conversations with the fact that we have two-dimensional presentation tools like blackboards and computer screens, but we would like to do this in 3 dimensions. We can't quite get there, but we can do 2 dimensions, and this is the typical way of doing it. We have something called a light cone, and the tilt of this line relative to the time axis is at 45 degrees. Anything moving slower than the speed of light will be confined into the interior of this cone. Light rays will be running on the surface of this cone. Now, there's a special place here, right there, and each one of us is experiencing it right now, and that is the here now location. Everything that's ever happened to you happened in this past light cone. All the events that conspired to come to you had to have occurred here, or else you would not have experienced them. And everything that happens in your future is confined to this light cone. Once again, we're struggling with the limitation of a 2-dimensional presentation screen. Okay. Now we're going to see what happens when we present a flat map like the one we've just been looking at. If we add a concentration of matter or energy, and remember, matter and energy are related by Einstein's famous E = mc squared, we can pictorially present this as a displacement of the space-time mesh that we all live in. So in regions away from a concentration of mass, the mesh is flat, and the map of the type we were just looking at will pertain. But in the vicinity of a mass, let's say this is the sun, there's a distortion in both space and time. And we see a smaller distortion. Perhaps this is a planet and a smaller planet. And these distortions influence the trajectory of light and matter that come into such a situation. Here's another way to present this grid of space and time. And we merge these words. We have to be careful to acknowledge that when we're talking about these kinds of problems, this space-time mesh is a merged concentration of space and time. So here is a space-time mesh with no matter or energy around. And here's what it might look like if you could see it when you present, if you put some matter or energy into that environment. Now, Newton produced a description of gravity that has been really successful. We still use it to fly to distant planets and so forth. Einstein's contribution was to explain why Newton's gravitational model works. And in the process, he found that both space and time are distorted by mass and energy, as we've been saying. And here again, here's a depiction of the sun altering the space-time in its environment, and the light rays that might also have gone through this neighborhood in a straight line are now influenced by the distortion in this mesh, and they end up with a curved trajectory. This is true for matter and energy. That's what we call gravity. And the famous physicist John Wheeler said that space-time tells matter how to move, and matter tells space-time how to curve. So these are compatible, connected issues. What does space-time look like when there's energy in the neighborhood? So we are going to extend the map that I just described into a different format. And when we do that, we will experience what happens when you try to, for example, draw a map of the sphere of Earth on a two-dimensional surface. So this is to introduce you to the idea that there will be distortions in the drawings that I'm going to show you, because we're trying to project three-dimensional information into fewer dimensions. This kind of projection of a sphere onto a plane distorts the relative size of polar objects compared to more equatorial objects. This Mercator projection makes it look like Greenland is dramatically bigger than Australia. That is not the case. There's Greenland. This is the way the map shows it. In reality, Greenland is a third the size of Australia. So it's more like that in reality. So be prepared for distortions that are going to occur because of mapping that we're going to exploit. Now, let's talk a little bit about black holes. It's part of the title of this talk. And these are massive objects, and they exhibit a characteristic not seen with other celestial objects. They have what is called a horizon. The interior of the horizon is cut off from the universe we live in. It's a sphere around a black hole through which, if you travel, you can never retreat. So the presence of a horizon is unique to black holes. And in the center of the horizon is the singularity where all the energy associated with what has entered the black hole is all concentrated. So you should also know, in spite of their mysteries and so forth, black holes are quite simple. They're characterized by their mass, their charge, their electric charge, and their properties of rotation. That's all you need to describe the black hole. And we'll get into this in a bit. Here's a depiction, a cartoon of what a black hole, a massive black hole, can do to the space-time mesh it bends it so dramatically that a horizon forms. And I'm going to show you that that's depicted by this green circle. I'm going to show you an example of how a horizon can form in a simple situation you might encounter. Let's say you're out on a lake, somebody drills a hole in the lake and water is draining into that hole. And you have a motorboat of some kind that has a maximum speed. If you're far from the hole where the water is draining, you might not even notice that the lake is draining. But if you come close to the drain place, you'll see water flowing into the drain, and that water has a velocity. If your boat has the capacity to exceed the velocity at which water is going down this drain, you can stay safely outside of this horizon that I drew to indicate that you're safe in this region as long as you can overcome the speed of the water. If you can't, if you go inside of this circle where the velocity of water flow exceeds the velocity of your boat, you're doomed. You're going to go down the drain. This is the kind of thing we're thinking about when we think about black holes, except it's space-time that's flowing into the hole, and your ability to stay safe depends on rockets or orbiting around the black hole outside the event horizon. Now remember, a black hole is a three-dimensional object, so we are once again limited in how we draw artwork to depict what experiences you might have. Now, what I'm going to show you has a lot of conceptual challenges. I will try to emphasize the key points, keep those in mind, even if the artwork doesn't fully convey what I'm trying to tell you. So here are Alice and Bob. Here's that map we drew early in this presentation, where Alice is in Boulder and Bob is in Longmont, and time progresses upward. And neither one of them are moving. Remember that light rays move at 45-degree angles because we've picked time to be in seconds and position to be in light seconds. So now here's Alice. She's not moving, but her trajectory points upward because time is carrying her along in this space-time map. Same thing for Bob. And Alice sends Bob a message, and that light message will travel at a 45-degree angle. He can then respond to her, and she can respond to him. And as we go through this presentation, you're going to see lots of examples of these kinds of rays propagating from point to point, indicating that Alice and Bob are using light to communicate. Here's the light cone for Alice, drawn in 2 dimensions, and similarly for Bob. Now things get more complicated if we introduce mass into the neighborhood. So, and this is, by the way, Einstein's compact mathematical notation. I always show this because to me, it's like a piece of art. If you stare at it and you have some technical background, each of these points represents an enormous amount of complexity, but it's a simple, elegant way to tell his story. And this is what it's depicting. Okay, so here's our distortion induced by mass or energy changing the space-time in the vicinity of some large object. And here's a simple version of a black hole. The center has a singularity where all the energy and matter that fall in all end up in the singularity, a microscopic point where everything is the atoms and it can't exist, nothing exists in that region. And it's surrounded by a horizon. And we're going to put it on our map. And we're going to look at different trajectories of light, depending on how far away they are from the influence of the black hole. So here is a light ray number 1, that travels just skimming over the surface of the horizon, and its trajectory is distorted just like is depicted here. Trajectory 2 is farther away from the black hole, and it suffers some deflection, but not nearly as much. And then 3, the same thing. And a far away light beam is unaffected completely. Now, there's a way to draw this, and this is where we're going to get into the distortions of maps. We're going to take this map, which is a 2-dimensional thing you might be comfortable with, and we're going to put it into what are called hyperbolic coordinates. And I'm going to show you how each of these items transfers from this map to this map, and I'll remind you about what happens when you take a globe and try to flatten it. There's going to be distortions. First of all, we'll ignore that half of this drawing. This drawing has a name, by the way. This is called a Kruskal diagram. Kruskal was a scientist in the starting in the 1950s who developed this concept. Others invented it almost the same time, but they did not know about each other. So let me show you now how to map from this depiction of space-time being altered by a black hole with a horizon, how it maps onto this version in other coordinates. In this case, the past and the future are just 2 different places where we go vertically on the time scale. In this map, past is here and future is here in a very special way. Here's what light ray number 1, this one, here's how it maps to this new Kruskal diagram. Its trajectory is altered as it goes past the black hole. This is light ray number 2, number 3, and number 4. Each of them appears to be curved on this map just because of the distortion that the map induces. Now let's identify some other important locations from our 2-dimensional map here to this Kruskal diagram. This dotted line is the horizon. This circle, or this sphere around the central singularity, gets mapped into a straight line. A sphere gets mapped into a line. That's the horizon. And the singularity, the single point in the center where all matter falling into a black hole goes to, that becomes this curved line, and I've depicted it with dragon's teeth to indicate this is, if you touch this area, you are dead. So our map now looks like this. We take this version and map it here, and we have the past and the future, the horizon and the singularity. This is the kind of distortion I was alerting you to. Now, this blue line that I just added is a line indicating a constant time, just like a vertical line on this map is just a straight line. On this map, it's also a straight line. And the closer it comes to this area here, the farther in the past it is. And the closer it comes to this line here, the farther in the future it is. So here I'm showing time advancing from the past to the future. Each instant of time is depicted by a line. This is sort of like a windshield wiper sweeping from the past over to the future. And if you look at this line when it's here, you're looking at the infinite past. And if you are looking here, let me get myself out of the way. If you are looking at a line that's close to the horizon, that's the infinite future. So here's our Kruskal diagram again, and I just put a small version of our original map here just to remind you of what that looks like. So here's the Kruskal diagram. And we're going to take a look at it in more detail. I'll remind you that any light ray travels at 45 degrees on this map. And we have a horizon, and we're going to have light cones, just like we saw a few minutes ago. And this quadrant here is all of history, because it goes from the infinite past to the infinite future. And it has all space in it as well. I'll show you more details in a second. So if we pick this line, we could say just notionally, this is the time of the dinosaurs. Anywhere along this line is, say, 100 million years ago. And then we have ancient Rome. Anywhere along this line has the same time. And this is 2,000 years ago. And here's a modern time, same thing. We're just advancing into the future as these purple lines sweep like a windshield wiper. Let's remember also that this green dotted line is the horizon. This is the danger zone. If you pass through this line, you're now into the interior of the black hole, and your future will encounter the singularity and you will not survive. Now let's talk about these curved lines. Like here, these dotted lines. Anywhere along this line is a fixed position. So if you start here at, let's say we start here, this is some place where there's dinosaurs because they were intersecting the time 100 million years ago, and there's some place where there were dinosaurs, and if you don't move, your time will carry you along this dotted line. As time advances, you will sweep from ancient times to modern times. Not far from where I live, there's such a location. We have, in the city of Denver, we have dinosaur footprints. And those were made 100 million years ago, and they've stayed in the same place as time has progressed. Now let's have Alice and Bob join the party. Here they are. Here's a line, this straight line, remember, is a constant time. So Alice and Bob are at different locations, because remember, these curved lines are locations. So Alice is at one location, Bob is at another, and no one is moving on this map. We just see them carried along by time, just like we did in our original map. So when we had the original map, Bob and Alice appeared to move only because time was advancing. And that's what we're seeing here. Now, let's go a little deeper. Here's the light cone for a traveler as they travel. If they don't move, their light cone, the region of space-time they can access, will move simply because time is advancing. And if they get to this point, they can send a signal through the horizon. This is the horizon, this green dotted line. They could send a light signal through, and it will go into the singularity. Or they can send a signal forward, and it'll just go out into space and never cross the singularity. The same is true for their motion. If they were brave enough to decide to not follow this curved line and drift through the horizon, they too would encounter the singularity. So we're showing an inward directed directed light beam goes that way, and an outward directed light beam goes that way. And in most of the cases I'm going to show you, Alice and Bob are using a rocket to stay outside the horizon. The gravity of the black hole would otherwise pull them through the horizon and they disappear. If you're inside the horizon, the light cone still works to depict your future. But notice if you're at this location, or actually any location above this green dotted line, your future is entirely dictated by this cone. And the only place you can go if you're at this place and time is to the singularity. If you touch this, you're at the singularity. So if you're outside, you can make a decision to go to the singularity. But you can also make a decision to survive. But if you're in this region between the horizon and the singularity, you have no chance to change because you cannot exceed the speed of light to try to escape. All right, so now we're ready to witness Alice and Bob communicating. So remember on our original map, she could send him a light beam and he could respond and so forth. The same thing is going to apply here. Remember, no one is moving. They just appear on this map because time is advancing. So at early times, here they are, and Alice can send Bob a message. And then Bob could respond. And Alice can send back to him, and Bob responds, and Alice and Bob. So they're sending communications back and forth. Neither one of them are moving. And we can see how light rays propagate near this black hole. And once again, the reason we distinguish this from any other kind of celestial object is it has a singularity and it has a horizon. Okay, now let's see what happens if we approach the black hole. If we get closer, this animation shows you what happens to positions as they approach the horizon. The inbound space, let's say you decide you're going to travel toward the horizon, you suddenly become converted into a trajectory that leads you to the singularity. When Einstein first announced his equations and people looked at them, they noticed this possibility of something weird happening at a horizon, which was a whole new concept. This is back in the 1920s. It took 30 or 40 years to finally interpret that mathematics to see this kind of behavior. So in a sense, your future, if you're inside the horizon, your future is not a time, it's a place, and that place is the singularity. So once again, here are Alice and Bob hovering above the black hole. There's the singularity and the horizon, and they're safe as long as they have fuel to keep from falling in, or they could go into orbit. It's just easier to depict it here as using a rocket to overcome the influence of the black hole's gravity. If they shut off their rocket, the gravitational force is going to drag them through the horizon. And let's watch what happens when we do this. Remember, over here is past long ago, and here's the far, far future. So Alice and Bob are using their rockets to stay on these curved lines, which mean they're not moving relative to the hole. They're maintaining their position. Now we're going to delve into some questions. Before we start, Alice and Bob are going to send messages back and forth. So this dotted line now is some far time in the past, and Alice sends Bob a message. And they agree, they're going to do experiments. Now time has advanced, and Alice sends Bob another message, and another message, and another message. And the question is, how are the messages that Bob is receiving, what effect occurs if Alice decides to depart from this fixed position and head toward the horizon? So Bob could send her a message. Now there's some notes out here. I'll let you read those at your leisure because I want to make sure we get through all the charts today. So now let's do an experiment. Alice announces she is going to cross the horizon and sacrifice herself for the good of science. She sends that message to Bob, and she keeps sending messages to Bob. And I've depicted the times here when she sends the messages. So say 50 seconds before she decides to shut off her rocket, she sends a message. And then 30 seconds before and 10 seconds before and so forth. Now notice what happens here. When Alice sends a message at this time, remember that this straight line represents a particular time, Bob receives it at a time far in the future. This dotted line is, let's say, at 500 seconds after the experiment starts. Alice sent it here 10 seconds before the experiment starts. So there's a time delay, and we know about that. You know, it takes time for light to propagate from place to place. Nothing surprising about that. But at this point, Alice decides to shut off her rocket engine, and her trajectory now heads toward the horizon. She leaves this curved line, which is a fixed position, and she's drifting toward the black hole. Now, if she sends a message from this location to Bob, notice that Bob is going to receive that message far, far in the future, because he's continuing to maintain his position on this curved line. And this curved line is going to carry him way out in that. Let me get this out of the way. His trajectory, his fixed position is going to carry him over here. But as he travels, the time intervals get compressed because this line is infinite time in the future. So when Alice sends a message, Bob is going to get it far, far in the future. And her next message is this red line. And she sends this message just as she crosses the horizon. When will Bob get that message? He will get it at time infinite. That is, he will never get that message. The reception of that message will be delayed because he's maintaining his position on this curved line. So to summarize, as soon as Alice leaves her fixed position and drifts toward the black hole, the influence that the mass of the black hole has on the advance of time can then be detected. And gradually, Bob will see her clock slow down. It will take an infinite amount of time for him to receive the signal that she sends just as she crosses the horizon. So he sees her clock red shifted. The light signal he gets is more and more red. And if she sends a message after she crosses the horizon, it never gets to Bob because a broadcast she makes from this position in space and time is going to encounter the singularity. So in effect, Bob will never see her cross the horizon. It looks like she slows down and freezes on that surface, and the signals she sends are so redshifted, eventually he can't detect them because the peaks and valleys of the waves she sends never get to him. Now, what does he observe about her when this happens? Not only does he see her clock slow down, he sees her compressed and flattened on the surface. So her original size, he observes, gets crushed down, and he sees her flattened on the surface, and she never moves. Now remember, Alice, let's talk about what happens to Alice. This is going on. So Bob is sending her messages. She has chosen this trajectory. She's going to cross the horizon right there. She will continue to get his messages. They will be blue shifted, that is shifted to higher frequency because of the influence of the gravitational field of the black hole. She can't respond to him, but she can keep seeing his messages. Just like she will continue to see starlight propagating through the horizon to her. If she looks outward after she has crossed the horizon, she will see starlight, blue shifted because of the influence of the mass of the black hole, but she'll also see Bob's messages. Now, what happens if both Bob and Alice decide to enter the black hole? Here's Alice's trajectory. I've already shown you this. She deviates from her fixed position and drifts here to the horizon. Remember, this is the horizon. And let's say Bob decides he's going to enter the horizon as well. So if they were communicating, Alice sent a message to Bob and he responded, and then he receives a message back. Let's see how this progresses. If Alice sends a message to Bob and he has decided to enter the black hole, he gets that message at the same time she crosses the horizon. Remember, this line is the horizon. So it is possible for Bob to get a message just before she crosses the horizon, but they both have to be crossing the horizon for that to happen. Once they're inside, the geometry of the Kruskal diagram shows that it's still possible for her to send him a signal. But can he respond? It depends on the timing. If she sends him a message and he responds, and the time it takes the message to get back to her exceeds the time that she has before she enters the singularity, she'll never get that message. The power of this drawing is it lets us explore those kinds of limitations. Now, that's not all. If you want to explore the interior of the black hole, you have to survive what are called tidal forces. And here's what goes on with tidal forces. If we take this astronaut and he has a wrench in this hand and a wrench in this hand, and he lets go of them, because everything is falling toward the center of Earth, in the case of an astronaut, the trajectory, this right-hand wrench will fall along this line, and his left-hand wrench will fall along this line, and in fact, they will start coming together. And this is what we call a tidal force. If you release objects in Earth orbit, they actually, if you do it carefully, you'll see they start moving toward one another. What's more, his feet experience more gravity than his head. So there's stretching and compression. And this is what would be experienced by our friend Alice in extreme. That is, an astronaut that gets too close to the event horizon of a very massive object like a black hole is going to get squeezed and stretched, and we call this spaghettification. Now, we do have some math. A little bit of arithmetic we can show you about survival rates. It turns out that relatively small black holes are more dangerous. The curvature of the horizon has a smaller radius. And that's because here we're looking at, say, the Milky Way black hole, 4 million solar mass black hole. Your time between crossing the horizon and hitting the singularity is about a minute if you venture close to the black hole at the center of our galaxy. But forces on your body, the tidal forces on your muscles and tissue, mean you would only survive about 9 seconds. If you go to a supermassive black hole, a 20 billion solar mass black hole, the curvature of the horizon is much smaller, and you have several days that you could survive inside the horizon. Sorry, the time to disappear into the singularity is several days, but you have 13 hours to explore the interior of the horizon. This is all based on strength of human tissue. So I've taken you through the Kruskal diagram and shown you how to use it to determine how communication occurs between travelers who venture close to a black hole. And that's called causality. If I send you a message and you respond, how will that communication unfold? And we've also talked about the fact that if you're distant from the surface of the horizon and you watch a traveler, you'll see them freeze on the horizon and disappear because of the redshift associated with the gravity of the black hole. And we've done this without math. So I've got some links here. Everyone will have access to these charts. If you're interested in contacting me, there's my email. If you want to look at other lectures on similar topics, there's my YouTube channel. I also lecture at Colorado State University here in the States. And we have, there's a vast array of adult education materials that you might be interested in if you want to look at the program. And that's what I had to say to you today. And let's open it up for questions.
Well, thank you very much, Ed, for a fascinating talk and beautifully clear in terms of your explanation of some quite complex concepts. Can I hand over now to Dave Baker, please, who will frame the questions for you. We have quite a number to get through.
Okay.
Okay, Ed, we have a number of questions here already. So I'll start off with, I'm not sure any of these are actually going to be simple questions, but we'll start off with the shorter ones, perhaps. This is from David W. How can you know if a black hole, hang on, I'm just losing this off my screen. How can you know if a black hole is spinning if no information can exit the hole? Okay,
so a spinning black hole will, and we think virtually all black holes are spinning because of the theories of formation. It seems unlikely that a black hole could come into being without spinning. But we won't look at anything coming out of the black hole, but we can look at the accretion disk that's around the black hole. Everything I've said today assumes a very simplified version of the real environment of black holes. In reality, they are surrounded by an enormous amount of dust and debris, some of which is going to be sucked in, some of which is going to be ejected. But all that material is outside the horizon, and we can see the rotation. And I will give you 3 letters that you could pursue if you want to follow up on this. And these are the letters E, H, and T. If you type that into Google, you will be connected with results from the Event Horizon Telescope, which is an international activity that has gone on for many years, where they actually took a picture of the accretion disk around the black hole, and you can see the distortion associated with the rotation of the black hole.
Okay, thank you for that one. Second question from Angus. If you were inside the event horizon, but looking outwards from the singularity, what would you actually see?
You would see starlight and the glow of the accretion disk that I just talked about. And if you had a companion who was outside the horizon and they were sending you light signals, you could see all of that. You can see inbound light altered by the mass of the black hole, but you can see light coming from the rest of the universe. And the situation for a spinning black hole gets more complicated. You actually would see essentially mirages of incoming light. So if you're looking outward, I expect to see an amazing array of distorted images.
Okay. So the next one is from Patrick O'Donoghue. Why are the light cones upright, i.e. in the same orientation, in both Kruskal and normal space?
Oh, that's a great question. And the reason is that Kruskal worked very hard to make that happen. The coordinate transformation, that's what technically it's called, to go from the first map I showed you to the Kruskal map, was designed so that the light cones have that property. You can also look at Penrose diagrams. You might want to look at that. The same thing applies. Penrose diagrams are a slightly different version of what Kruskal did. And in Penrose's version, the light cones are erect. That's a desirable feature of these coordinate transformations, is to have the light cones appear as they do.
Okay, so perhaps a slightly lighter-hearted question from Jack. It says, how accurate on a scale of 1 to 10, 10 being very accurate, would you say the film Interstellar is in depicting black holes?
The great thing about Interstellar is that Kip Thorne, who just a couple of years ago won the Nobel Prize for his work on detecting gravitational waves, Kip Thorne was the producer and idea author, the storyteller behind the movie. And if you get his book that describes the making of the movie, you will find that there are 3 categories of science used in the movie. One is science we know is true about the physics of black holes. The second is science we think is right, but there's more work to do. And the third category is science that could be right. We don't currently know of a reason why it can't be right. And the movie Interstellar is just one tick away from science fiction. I mean, it is based on real behavior of real celestial objects, including the neutron star that's introduced. They did make some modification for visual effects, but in principle, almost everything in Interstellar is real science.
Okay, thank you for that one. Next one from Sami Nofal. According to Einstein's general relativity theory, gravity will curve space and time. Does this imply that the Earth gravity has any significant effect on the atomic clocks on the GPS satellites? Does this effect vary from different orbiting objects, for example, between the ISS and the newly launched James Webb Telescope?
A fantastic question, and the answer is GPS would not work except that we used Einstein's theory to set the clock rates on the satellites and know that those clocks advance at a different rate than clocks on planet Earth, because the satellites and the surface of Earth experience different gravity. There's a difference of something like 350 nanoseconds per day in clock rate between the GPS satellites and the clock that's in your cell phone. Otherwise, the GPS would not work. So that clock correction is essential, and that's another confirmation of Einstein's theory that GPS does work.
Great stuff. Good answer. Another one from Jonathan. If we assume that Bob flashes a green light every second in his time, what will Alice see as she gets closer and closer to the event horizon? Will she see the time between flashes go to 0?
She will see blue shifting. Yes, the color will change, and the interval between the flashes will get shorter for her. When she sends a signal to Bob, the interval between her flashes gets longer and eventually gets to be infinite. And the color of her, let's say she's using a laser, the color will shift toward the red. So both of them will see an effect.
Okay. So the next one from Lass is, can Alice send a message from the inner side of the event horizon towards the past to Bob in the past?
No, first of all, she cannot, you cannot, if you think about those light cones, it looks like an hourglass. You can't send a message to your past. You can only send messages in the upward opening half of the hourglass. I should have mentioned that during the lecture. The past, that light cone that points downward, just depicts the events that influence your life here and now. But you can't alter them. You cannot send a message to your old self.
Okay. This one from Mike Wilshire. Your diagram indicates a waterfall effect as you enter the horizon. Does that mean things get faster? So does light travel faster, or is space also compressed so it does not?
So light travels the same rate in all circumstances. What that drawing of the lake tries to depict is that space-time gets drawn faster and faster toward the singularity. If you contact me, you have my email address, I'll send you a link to the work of Andrew Hamilton, who is a professor here in Colorado, and he has wonderful animations of these kinds of challenging conceptual ideas. So write to me and I'll send you a link to Andrew Hamilton.
Okay, thank you. Question from Steve Cheel. Is the singularity of zero size? And if not, how big is it? Or how could we tell how big it is?
So to understand that, we need to extend Einstein's theory. We don't know how big it is, but it's my normal comment to students is it's the smallest thing in the universe, that singularity. It's a geometric point. And I'll just pose a question and answer it as well. And you might ask, well, where did all the energy go from the matter and radiation that's fallen into that black hole? And the answer is, it's all invested in bending space-time. It takes energy to bend space-time. The material, atoms and such, that fall in, just like Alice, everything gets spaghettified as it falls toward the singularity. Atoms can't exist. The components of the protons and neutrons can't exist. They're all stripped apart and destroyed. And all that energy is invested in curvature at the singularity.
Okay, Ed, I think, unfortunately, although we have quite a few questions left, we're going to have to call a stop at this point because I know you have another lecture that you need to get to. So I think we'll finish at that, and I'll hand over to George to tie everything down and finish the lecture. Thank you very much, Ed.
Okay, thanks, Dave, and make sure I get a copy of the questions so I can compose answers.
We will do that. Well, thank you very much indeed, Ed, for a great presentation. From my perspective, it takes some real skill to explain such complex concepts with such elegant clarity and simplicity. So well done. And actually, the QA in many ways was very, very impressive as well. Every question was a model of clarity in the response. So thank you very much indeed, and we hope you can move on to your next appointment without any major problem.
I want to thank you for the opportunity to speak to this a very large audience, and I look forward to communicating with people who do have questions, and it was a great experience for me as well.
Okay, so just to draw your attention to some future events, from Anglian Coastal Local Network. On the 8th of March, for those of you who travel regularly on the local railways, Dr. Felix Ngobega from the University of Suffolk will talk about improving the Ethernet train backbone. And on the 29th of March, Sandeep Day of University of Essex will talk about machine learning and how these will make smartphones smarter. For more details of these events and future events, look at our community site. You can see the URL there, NGEX at the IET Local Networks EA1. So without further ado, thank you very much for joining us this evening, and hope you have a great evening.